Okay, we'll start problem 17 here. It says to determine if f is a rational function and then state its domain. A rational function is a function in the form polynomial over polynomial. Okay, so part A would be a rational function, right? Because these two things are polynomials and I'm dividing them. Okay, now the domain is all the x values. So I know I can't divide by 0. So if I set the denominator equal to 0 and then solve, so the denominator factors as x plus 5 times x minus 2. And if I set those two things equal to 0, I get x equal -5 or x equal 2. Now that's what I don't want. Okay, I can use any number, just not either of those two. Okay, that's a polynomial. Excuse me, that's a rational function because I got a polynomial over a polynomial. In part B, is this a rational function? The answer is no, because 3 minus the square root of x, that's not a polynomial. Okay, because I can't have fractional exponents with polynomials. So the answer there would be no. Now the domain is where x squared plus x can't be 0. And that's going to factor nicely. So if I factor on x, I get x times x plus 1 equals 0. X would be 0 and x equals -1. That's what I don't want. Okay, so I can let x be any number, just not 0 or -1. Okay. In problem 18, they want us to identify the horizontal or oblique or vertical asymptotes that are on the graph. Also state the domain of f. Okay. So let's see. You're going to have two vertical asymptotes. Use dotted lines whenever you're drawing an asymptote. That means that the graph is going to approach that boundary, but it's never going to get there. Okay? And it looks like x would be 5 is the equation of that dotted line, and then x equal -5 over here. So you're going to have two vertical asymptotes at x equal 5 and x equal -5. There's also going to be a horizontal asymptote at y equals 4. Okay. By the way, whenever you're writing down equations of asymptotes, be sure that you're writing them as equations. So don't just write 4. Okay, because 4 looks misleading. Like, are you talking about x equal 4? Because x equal 4, that's different from y equal 4. Okay. So write down y equals 4, x equals 5, x equals -5. Okay. Now the domain of this function is asking for the x values. So we get the vertical asymptotes by knowing the domain of the function. So the domain will be all real numbers except for 5 and -5. So because you're throwing away 5 and -5, you're going to have two vertical asymptotes at x equal 5 and x equal -5. Okay. Problem 19 is where they want us to find the vertical or horizontal asymptotes. Okay, so again, the vertical asymptotes are when I set the denominator equal to 0 and I solve. So x squared minus 9 equals 0. If I solve that equation, x squared is 9. So then take the square root of both sides, x would be plus or minus 3. Okay, I'm going to have two vertical asymptotes on this graph here at x equal 3 and x equal -3. Again, make sure those are written as equations. And then to get the horizontal asymptote, so I'm comparing the degree of the top to the degree of the bottom. The degree up top is 1, the degree meaning the largest power of x that I see, okay, divided by a degree 2 polynomial. Okay, so 1 is less than 2, right? So y equals 0 is going to be a horizontal asymptote. You're always going to have y equals 0 as the horizontal asymptote whenever the degree up top is less than the degree down under. Okay? In part B, we want to get the vertical or horizontal asymptotes there. So when I set the denominator equal to 0, X squared plus 4x minus 21 equals 0. That's going to factor nicely as x plus 7 times x minus 3. So then when I set each of those equal to 0, x equals negative 7 and x equals 3. That's what I don't want, right? So I'm going to have two vertical asymptotes at x equals negative 7 and x equals 3 because I can't divide by 0. Okay? And then now this graph is going to have a horizontal asymptote on it. How I know that is because if I compare the degree up top to the degree down under, I have a degree 2 polynomial up top, and I'm dividing by a degree 2 polynomial down under. Okay? So I'm going to have a horizontal asymptote. It's not going to be at y equals 0, though. It's going to be at y equals some other spot. And to find out where, I'll need to divide. Okay? Now I'm dividing by a trinomial, something with 3 terms, so I can't use synthetic division. Synthetic division, you can only use that when you're dividing by a binomial. Okay, so like right here, we're using synthetic division. Okay, so yeah, I'll go ahead and set up the long division calculation. The denominator is going to go out in front of the division bar. The numerator is going to go underneath the division bar. And I'm ready to divide. If we have a 3 up top, 3 times x squared plus 4x minus 21, that's be 3x squared plus 12x minus 63. We're subtracting those. Okay, so I can switch all the signs, or usually what I do is I'll throw a negative in front and have parentheses around the expression there. So 3x squared minus 3x squared, that's 0. 0 minus 12x is minus 12x. And then negative 1 plus 63 is 62. Okay, now that's my leftover. Okay, the complete leftover information would be a fraction that you're going to add to the quotient. So I'm going to say plus, the complete leftover would be negative 12x plus 62 divided by x squared plus 4x minus 21. Okay, now I'm going to have a horizontal asymptote at y equals 3. And how I can get that is I can start by looking at the leftover and compare the degree up top to the degree down under. I have a degree 1 polynomial up top divided by a degree 2 polynomial down under. 1 is less than 2, right? So y equals 0 would be a horizontal asymptote, but I'm going to start with y equals 0, and then I'm going to add 3 to that. So ultimately, y equals 3 becomes the equation, the horizontal asymptote. Okay? Now, a very quick way to get the answer would be to compare the leading coefficients in front of the terms. So I got a 3 in front of x squared up top, a 1 in front of x squared down under. 3 over 1 is 3. Y equals 3, the end. Okay, so like I could already know before I even divided here that my answer is going to be y equals 3. Part of what I'm going to test you over, though, is that you can divide completely and divide correctly. Okay, so like I'm going to want to see this, division calculation done here in the problem, show me how you get y equals 3. Okay, so be sure that you know how to do that there. Okay. Here's another one. Problem 20 is where they want us to find the vertical or oblique asymptotes for f of x equal 2x squared minus 5x minus 2 divided by x minus 2. Okay. So the domain is all real numbers except for 2. Right? I can't divide by 0. So because I'm going to throw 2 away, I know that I'm going to have a vertical asymptote at x equals 2. Okay? So the vertical asymptotes come immediately just by knowing the domain of the function. Okay? Now this function is going to have an oblique asymptote. An oblique asymptote is an asymptote, but it's got like a slant to it. Okay? Now how I know that this is going to have an oblique asymptote is because if I compare the degree up top to the degree down under, I have a degree 2 polynomial up top divided by a degree 1 polynomial down under. 2 is bigger than 1, right? So whenever that's the case, whenever the degree up top is bigger than the degree down under, you're going to have an oblique asymptote. An oblique asymptote is like a slanted boundary there. Okay? So I'll need to divide. X minus 2 is going to go outside the division bar, and then 2x squared minus 5x minus 2, that'll go underneath it. I suppose that for this problem you could use synthetic division, right? Because you're dividing by a binomial, something with two terms there. So that would be fine. You know, I've already got the long division set up here, so I'll use that. But we're all set up to divide now. So let's see, if I take 2x times x minus 2, that's 2x squared minus 4x. And I'm subtracting those. Okay, so 2x squared minus 2x squared, that's 0. Here's negative 5x plus 4x is negative x. And then I can bring in the minus 2. And I can divide again. So if I tack on a minus 1 up top after the 2x there, negative 1 times x minus 2 is negative x plus 2. I'm subtracting those. Okay, so negative x plus x, that's 0. Negative 2 minus 2 is negative 4. Negative 4 is my remainder. Okay, the complete leftover information is always going to be a fraction that you're going to add to the quotient. So sometimes I see where students won't have a plus sign there. Don't do that, because then it makes it look like you're multiplying things. You're not multiplying anything. Okay, so we need to add the leftover. The complete leftover would be where you take negative 4 divided by x minus 2. Okay, now there's going to be an oblique asymptote at y equals 2x minus 1. So I'm going to ignore this leftover. Okay, and I'm just going to write as an equation y equals 2x minus 1 there. Okay, again, the reason why I'm ignoring this is because if I compare the degree up top to the degree down under, the degree up top is 0, I don't have any x's up top, divided by a degree 1 polynomial down under. 0 is less than 1, right? So y equals 0 would be like a starting place, and so I'm just going to add 2x minus 1 to 0. So I get y equals 2x minus 1. That'd be the equation of the oblique asymptote there. Okay? Now, you guys won't have to ever worry about situations like this where I got a rational function and the degree up top is 2 or more compared to the degree down under. We do have boundaries with those. They're not lines, though. They're curved boundaries. Okay, so you guys are only going to be working with linear boundaries. So vertical asymptotes, oblique asymptotes, and horizontal asymptotes. Okay. All right. We'll stop the video right there, and I'll pick up with problem 21 in the next one there.